Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello. So it's my pleasure today to have here Darko Marinov, who is now an assistant professor at Urbana-Champaign, Illinois. And so before that, he got his PhD at MIT. And even before that, he actually was interning with us for 3 months. So we already know him for a long time. And he's been working on testing and how to improve it. So I'm actually looking forward to hearing his latest results today.
Okay, thank you. Thanks, Nikolai. Hello, everyone. Okay, so the latest results will be on this work that was done on automated testing of refactoring engines using something that I call test abstractions. I'll describe what I mean by these test abstractions. I'll be here talking, but of course the work was done actually by students. So here's the list of people who were involved in that. Brad Daniel, he's my PhD student. He was actually the main person behind this work. Then the others who helped, Danny Digg, Kely Garcia, Vilas Jagannath, and Yunyan Lee more recently. Also, the work was supported by National Science Foundations, by some grants, and then a gift from Microsoft. It was a small gift, so if you have more money to give for testing, it would be good. So what we wanted to look at was some testing of refactoring engines. So let's first see what these are. So refactorings are behavior preserving program transformations. So the idea there is that you want to change the code of the program, but you don't want to change its external behavior. The reason why people want to do this refactoring is typically to improve program design. You want to make your program easier to maintain or easier to use, and so on. So some examples involve things like rename a class. Maybe you're building an object-oriented program and you had some class that you called A. Now realize that A is really a bad name, and so instead of A, you should have called it an airplane if it models an airplane or something like that. So you simply want to go and apply this change across the program. Now you can do this manually, but it's kind of tedious to go everywhere in the program, find wherever that you had A and replace that with, say, airplane. So what you want to do is actually to automate this process. And refactoring engines are programming tools that actually automate these applications of refactorings. So if you say want to rename class A with airplane, you just go to the tool and point that that's what you want to do, and it goes automatically, traverses the entire code, and finds where to make these changes. And these refactoring engines are included in many modern IDEs. Here are examples from 2 open source IDEs from Eclipse and NetBeans. If you go in the top level menu, they actually offer these refactorings that can be applied. So on the left is Eclipse. They've started building their refactoring engine a few years before the one in NetBeans. So they have more of these refactorings, including things like renaming program elements, moving them, things like convert local variable to field, and so on. So NetBeans has somewhat fewer of these. And then Visual Studio also has a number of refactorings implemented, but I think even fewer. It has something like 4 or 5. We did not test Visual Studio just because it's not open source, so we didn't have easy access to that and to adding some changes to the tool itself to make it easier to test. So why did we want to test these refactoring engines? Well, one thing is that they are widely used. Programmers actually want to use the refactoring engines rather than manually making these changes through the program. Also, they are complex. It's kind of interesting to test something that's not simple. And they're complex in 2 dimensions. So first, the inputs that they take are complex. So what the refactoring engine does, it takes an input, a program, takes a source code, and then as the output, it also produces a changed source code. Maybe just say renaming a class. So the inputs themselves are complex, and also the code of the refactoring engine itself is complex. So it needs to usually perform some sophisticated program analysis to find whether it's fine to perform a refactoring and how to change the program. It then also needs to perform a transformation that actually goes in and makes the changes in the program. And then what's also important is that a bug in refactoring engine can have severe consequences on the development. Namely, if there is some bug, it can sometimes silently corrupt large parts of the programs. If you're a developer and building some program, and if you apply refactoring, it may happen that this refactoring engine just goes and silently corrupts something. Say, instead of replacing your class A with airplane, it goes and replaces with something else, and now things don't work. Sometimes you can find this easily because the output program does not compile. So if there is a bug in refactoring engine, you can easily detect that there is a bug. But sometimes that's not the case. So basically you find a bug that's very kind of hidden, and it's as unpleasant as finding a bug in a compiler itself. And kind of last but not least, why we wanted to test refactoring engines was because they contain bugs. If you do some research on testing, usually you try to look at something where there are bugs so you can say that you found bugs. But more importantly was because people use this, and so it looked like a significant and complex application and something interesting and challenging to test. So here's an example how refactoring looks like. This is an example that I'll use throughout the talk. There's this refactoring that's called Encapsulate field. And so what it does, it replaces all fields accesses with appropriate accesses through the getter and setter methods. So on the left here, we have an input program, just a small program for illustrative purposes. So it has only one class A. It has only one field, this F. And there is some method M here that accesses this field F, right? So it reads F and then multiplies maybe with some I and then writes that to F. Now what we want to do here is, say, to replace all these accesses to the field F with actually using getters and setter methods. The reason why we want to do that, again, is to kind of improve the design of our program. Usually it's a bad practice to access fields directly. It's much better to access them with the getters and setters. Now in this simple example, these fields are accessed from the same class, so it's fine to access them there. But in general, these field accesses could have been from different classes. Now we can use a tool to do this. We would just go to the field F. We would click there and say encapsulate this field. And what the tool would do is actually make these changes shown there on the right. So this on the right is the output program. And it would make 5 changes. So first it would add this getter method. So it would add this method here that just returns the value of F. Then it would add this setter method. So this is the one that can set the field F. So given some new value, it just sets this F. Then it would replace these field reads with the calls to the getter method, as this thing here. And then these field writes that were here, where F was set, it would replace those with setter methods. And then finally makes this field private such that if it was accessed from the other class, it cannot be accessed anymore. Okay? How many people here have used refactorings? Okay. Almost everyone. So here's some bug that we found in Eclipse. So here we have, again, a very similar program, input program on the left. In this case, we have 2 classes, one of which subclass is the other. And if we apply here encapsulate field, here's the output program that Eclipse generates. And as it turns out, there is actually a bug here. The bug is right here. And what happened here was that we had this effectively field write. We were setting the super.f to 0. But because the engine has some bug, it thought that this was getting a field F. So here's the output that it generated. It said somehow that you want to get the field F and then do something with it. As a matter of fact, this thing here would not even compile. What it should have generated should have been this, super.setf of 0. Here's another bug that was found in NetBeans. Here the bug is slightly different in that the output program does compile, but it's still, the refactoring was not applied correctly. Again, here's the input program and something small. We have one class with some one field, and there is some method, and then we are kind of reading actually writing to this field F by a somewhat weird way. We have these brackets around this. So we are setting the field F of some object A to 0, and we want to encapsulate this. And this is what the refactoring engine gives. So it properly introduces the setter and getter methods. However, it does not replace this access. It just leaves it as it was. So the bug again is here in this line. And what it should have done actually is generated this setter. So it should have been new of a.setf to 0. Sense? No? Yes? Nikolai doesn't think that this is a bug.
It doesn't change the behavior of the program, right? Maybe not the intention of the refactoring, but what is it anyway?
Okay. That's actually a very good question. I mean, what's even a definition of a bug in a refactoring engine? I guess part of what we wanted to do is to preserve behavior, right? So if you generated something whereby, when I run the program, I get a different value, we could say that that's definitely a bug. But if that's the only thing that you want out of a refactoring engine, then it would be very easy, right? I can just build,
It's outside of A, right?
Sorry?
In this case, M is in the class, so it has access to M.
Okay, yeah, I guess what...
Whereas when you're up, you don't have the visibility to it.
Okay, so I guess what Pelle is also saying that in this example, F is inside. Let me first answer that question, then I can go back to this other one. Yes, in this case, F is indeed inside. So you could even say maybe when you want to do this encapsulate field, you don't need to change the axes that are inside the class. It's fine to access those directly. You don't want to change them to setters and getters. But the same bug would have occurred even if M was outside. If M was outside and in another class B and it was accessing to this F, it would still not replace this. In that particular case, it would also have then a compile error because F field became private and you're trying to exit from outside. So that's kind of the answer to this specific question. But going back to this more general question, what is a bug in a refactoring engine? It's not only that you wanted to preserve behavior, but actually wanted to do the change that you wanted to do. Here actually an interesting example of something like this where we wanted to replace some fields and then the refactoring engine did not replace this. And actually that's the example. It was artificially created an example where we created something to show how a bug here may have big consequences. What they did there was some field here that was kind of measuring some temperature. And what we wanted to do here is kind of say for this set temperature, say if the temperature you want to set exceeds some limit, then raise some exception rather than exploding something somewhere. So if you want to do that, what that means is when you encapsulate field, you would start adding some behavior here of what you want to happen whenever you set this field F. And if you don't have all the fields to F properly going through this set F, then you could just miss something like that. So in our example, we would get some boiler to explode or something like that. But I agree with you that these examples may look somewhat like simple and artificial, and one may ask, is this really a bug or not? But usually you can construct some bigger bugs from these, going from these smaller, simple examples. Still see, Nikolai is still not convinced about that.
Then again, so if you say when you add behavior to the setter, then the bug will surface. But then again, it wouldn't be really a bug of the refactoring, but you have some other invariance then in the program which is violated. But I mean, if nobody writes that down, how can you blame the refactoring engines? So do you have a definition of what it means to be a bug for the refactoring engine?
Well, I guess definition what it means to be a bug. Okay, so I guess one way you could define that is actually going and implementing your own refactoring engine and saying, if this other one doesn't generate the same thing as mine, that would be a bug. So say for encapsulate field, the definition of encapsulate field, it says, it replaces all fields read and write with accesses through getter methods, getter and setter methods. So I guess here the point is that you should replace all fields read and write. Of course, you could have a different encapsulate field which says, I do not replace those that are within the same class. You have your encapsulate field outside of the class, in which case you could say, it replaces all axes that are outside of the class with getters and setters. So, the definition would be you could, formalize this, what it means, this thing here, and then check whether the output program really satisfies this property or not. This makes sense?
I think it's a bug in the sense it certainly violates the expectation. You expect everything to be replaced. And then you behave accordingly. You modify your program.
Yes, so if you run encapsulate field, again, you do expect that all the field X is very replaced with get and set. So if you add later on some behavior to these getters and setters, you hope that everything was indeed replaced.
So I understand now the definition of a bug. Is that actually also how you check for a bug, or how did you discover these bugs?
It's a very good question, so maybe I can postpone that for a few slides and discuss what were the oracles that we used for that. Okay, so then these were the examples, so maybe you can trust me so far that these are bugs. Maybe we wouldn't call them bugs. We can discuss that later on, whether these are really bugs or not. So one way of how we check whether this is a bug or not is get the same input program, say get this program, and then run it both through Eclipse and NetBeans. And if they would give something different, then we would ask the question, is there really a bug? Is one of them wrong because they are getting different results, or is it simply that your spec is non-deterministic and you can give any of these two? I think that was the way to discover this one, because if you get things that compile, those are actually the most problematic bugs. Because if something doesn't compile, if you go back here, if you just apply encapsulate field and you get this thing, it will immediately tell you that here it does not compile. I can just immediately see that something went wrong. If I give you a program that compiles and you make some change and it doesn't compile anymore, you know that went wrong. But here it's much trickier because everything compiles and it looks seemingly fine. Actually, you could even find that this is that it preserved behavior, but it still didn't do what you wanted it to do. Okay, so how does one test then this refactoring engine? This kind of the general setup. You get the refactoring engine. You give it some input program which you want to change. You give it what refactoring to apply, say encapsulate field or rename class or something like that. And what the refactoring engine gives you as the output is either a refactored program, as we've seen in these examples before, or it can instead give you a set of warnings and say, I cannot actually go and refactor this, I cannot apply this for several reasons. Say if you want to rename the class A to be called airplane, maybe there's already a class airplane in your program, then it would just say, I cannot create something with airplane because now obviously you're going to get two classes that have the same name and that's going to create some problems. Or it could say I cannot encapsulate some fields because you already have setters and getters, or maybe because field is accessed from outside, so once it becomes private, couldn't be done, and so on. So these warnings are kind of very refactoring specific, and the good engine needs to apply all these program analysis to figure out whether it's safe to apply refactoring or not before it actually goes and changes the program. So how do actually people test these refactoring engines? Both Eclipse and NetBeans have a number of manually written tests. So developers, so these engines care about their programs. So they go and write unit tests for that. So they write these input programs. So they kind of prepare the program, a number of classes that are referenced in a certain way. They also have the code that invokes these refactorings. And then they have the expected output. So this is either that they refactor the program by hand and say this is what you should get, or some set of expected warnings in case where you do want to test for the cases where you're expecting to get warnings. So these are all manually written tests, and then they're automatically executed. Eclipse, for example, uses JUnit for this. So they have over 2,600 these JUnit tests. NetBeans uses a different testing framework called XTest, and they have seemingly a much smaller number, 252. But the issue here is that it's not quite a fair comparison because the NetBeans has much larger tests. So they have kind of more like system tests where they go and execute many things at once. So even this number 250 actually is, there are many more things that are happening there than in any one of the small JUnit tests for Eclipse.
Do you have the number of lines of the test code?
I don't know that by heart, but...
Then each individual test, is it 10 lines, 100 lines? How
most of the tests are, interesting enough, are one line because all the test does is kind of... all that this test does, so when you ask the number of lines, there are two things to distinguish. There is like the code of the test and kind of the test input, right? So what is the file? So the code is usually just one line. You would say apply encapsulate field on some project P0 or project P1 or project P2 or project P3 and kind of check that the expected result is the same as E0 or E1 or E2 or E3. Maybe the size should be then more measured in terms of the program files. How big is your program input? Because this testing is most kind of data driven, right? So your input data are the program files, And the code to actually just apply the test is fairly simple. So, load the whole project, apply refactoring, and then check whether the output is the same as expected. And that's very generic. So you write that once, and then each test is just one line that calls the generic thing. Actually, not to go there, but each test actually has 0 lines because they use reflection and refer on the name of the test method to figure out which project to read. So the point there was that these people care about that, and so they built a large number of tests, and they'll still show that we are finding bugs in that code. So what we wanted actually to do here was to automate this testing. So rather than manually creating all these test inputs and then checking whether the outputs are correct, we wanted to automate both this input generation and output checking. So now a lot of testing research actually goes along the lines of, I'll give you this refactoring engine, and it's some big pile of code, and you'll somehow magically just look at this code and from there generate the inputs that could show bugs, or maybe your inputs that would achieve coverage or something like that. In this domain, however, it's very hard to do that. I mean, refactoring engines are just fairly complex to be able to generate test inputs for them. Inputs themselves are also fairly complex. You need to effectively generate programs. You need to generate abstract syntax tree that satisfies some syntactic and semantic constraints of valid programs. You have very strong preconditions on these test inputs. So we did not even attempt to do that. We did not want to look at the refactoring code and just from there automatically generate tests. What we actually wanted to do is something else. Here, so basically we made these assumptions that the tester has... Yes, Grigori.
Question.
Yes.
A very simple way to test appears to be the following. You can just take any program which has already been tested, which has lots of tests already generated, and then just apply refactorings and then run the tests in the original one, if you look at the refactored one, and you should see the same behavior, right? So that can be done in addition to these tests.
Yes. That's a very good thing. Yes, that's something that we did discuss. So basically you get an existing program, as you said, that has tests. Now you go and refactor that program plus its test, and then you rerun the test and see whether tests are still passing. Yeah, that's definitely something that can be done, something that we discussed. We did not do that. Sorry?
You still have to come up with the specifications yourself then. What you want to refactor.
Yes, but I guess in theory you could just traverse and apply all possible refactorings. So if I have a program with many classes, I could just say, okay, get any of these classes, try to rename it to some new name that does not appear there, or then try...
To a large program with lots of tests, you should have quite some confidence that the engine works, right?
That's true, except that you may miss many of the bugs that we found. If the programs that you have do not have certain kind of weird properties, if in your program you never use something like this, you're just not going to find the refactoring. You're not going to find this specific bug. Of course, then you could say, well, maybe this bug does not matter, right? If no real program would ever write something like this, then it does not matter. Actually, I didn't even know that this is valid Java, that you can put these brackets on the left side of an assignment. But the thing is, usually, when you go and try to look for these bugs are kind of social creatures. They tend to go together. So when you find some bugs somewhere, there are more bugs there. Actually, once we found this bug here in Encapsulate field, we actually went on there and found many more bugs. So even if this specific one looks like who cares, then there are many others that may be much more important. But yeah, what you suggested is kind of one way in which this testing can be done. We discussed that, but never did that. What we did was instead to look at this other thing here. So we made this assumption the tester kind of knows what inputs could expose bugs. So tester has good intuition for that. Say an example, if you want to encapsulate field, well, we could say maybe there are some problems if they're inherited fields. If some subclass is inheriting a field and then referring to that in some weird ways, that could potentially show a bug. So that's one important assumption sort of behind the work. And then the other one is that it's labor intensive to manually write many input programs. If this encapsulate inherited field requires you only to write one or two test inputs, that's fine. You can just go and do that manually and be done. But if it requires you to write, say, thousands of them, then it's very hard to go and actually manually generate one by one of these to check for that. So if you want then to take this approach, then the challenges become how to codify this tester's intuition. So if I already know where the bugs may be, how can I actually turn that into a way to automatically generate large number of test inputs? And then also how to automatically check that the outputs are correct if I start generating inputs automatically. And so the kind of general solution that I call for this problem is something I call test abstractions. So the idea of test abstraction is that they conceptually describe a set of test inputs. So the main idea there is that instead of manually writing a large number of tests, the user should write these test abstractions and then tools automatically generate tests. Again, if you want to test refactoring engines, rather than you manually writing a large number of these input programs, you just somehow want to describe what are the input programs that you want to generate, and then have the tool generate that automatically. And the claim that I'm making is this is useful not only for test generation when you want to generate this thing once, but also for maintenance. Say if you decide to make some changes in your test inputs, some changes in your code, if you need to regenerate this, if you use some these kind of test abstractions and you have descriptions of a set of inputs, then you can just regenerate this thing. Whereas if you were to manually generate, hundreds or thousands of them, you would need to somehow manually or to upgrade them all. We need to write some scripts to change all these tests. So if you do something like this using these test abstractions, then you're going to be automatically generating tests. But whenever you have that, then you have the issue of you need to check whether the code is actually working correctly or not. So namely, we run into this problem of test oracles. We need to have a way to automatically determine whether the execution was correct or not. And then also the other related problem is of this clustering. If we start now getting tests that do fail, we would like to group them such that they're usually due to the same fault, such that you don't need to explore all of them. Yes, Tom.
So the first 2, 3, the test abstractions, that sounds sort of like model-based testing.
Yes, but you need to have a different buzzword to get career proposal from NSF. So my buzzword is test abstractions. Yes, but you could call this model-based testing, I guess. That would be fine.
Is there some technical difference between these? Are these programs? Are these model programs? These test abstractions, they could be, or
they could be. The idea is, the test abstraction is a general term, and you can do whatever you want put there. So I would say that model-based testing is one approach to doing test abstraction. Usually, when you say model-based testing, people think of a certain models, right? They would think of finite state machines. Not necessarily different. People may use different models. But suppose that you want to describe some complex input such as Java programs. So would you call that a model-based testing? And what would be your appropriate model? Of course, you can do that. You can say my models are some grammars or something that describes what valid programs are, and this should be called model-based testing. I think that model-based testing usually, at least to me, means that you're generating some kind of sequence of inputs that you are giving to your program. At least in my mind. I don't know. Yuri, what would you think of model-based testing? Would you think of generation of complex inputs as model-based testing or not?
There are no clear borders.
Okay. This could have been easily called model-based testing. Oftentimes then if you do model-based testing, you kind of has test oracle embedded into the model, right? That the model not only helps you to generate inputs, but also to check the outputs. Whereas here, what I'll present, the model somehow does not embody what the correct output is. Okay, so that was sort of the general thing about the test abstractions or model-based testing or however we want to call that. And here's then the specific solution that we did for testing these refactoring engines. We've developed something that we call ASTGen. So this is a framework for generating abstract syntax trees. So this is a way for us to generate these input programs for testing refactoring engines. And basically what it does, it provides a library of generators that can produce simple parts of AST. And then there is a way to combine these simpler things and actually build larger programs. And so that was as far as the test inputs go. And then as far as the test outputs go, basically we just develop manually a variety of oracles. So There was no automation there in terms of automatically generating oracles, so that was manually written, and then you would just like automatically run them. And we have some ongoing work on this clustering, basically if there are failing tests to try to group them together due to their causes. So ASTGen was then the main thing that we developed, this framework for generating abstract syntax trees. And we had a few design goals for that. First, we wanted this to be imperative. So the idea there is that the tester can control how to build this complex data. Some previous work that I worked on, we've taken a declarative approach to that, where the tester would not describe directly how to generate complex data, but would only describe what the properties of the data was. So you would just describe what a valid Java program sees and maybe what specific properties you want it to satisfy, and then the tool will generate that. So here the approach is different, and then the tester directly writes how to build this data. We also wanted this to be iterative, which means that it can generate these inputs lazily, because oftentimes you can end up with thousands of them, or even in theory with millions of these inputs, so we don't want to generate them all at once. We wanted this framework also to be bounded exhaustive. So this is an interesting point. So the idea here of this bounded exhaustive is that you want to try all tests within a given bounds. So say if we want to generate the programs, we may want to say, well, we are going to generate the programs that have up to 3 classes, or we are going to generate expressions that have up to 3 levels of nesting, and so on. So you put some bounds on the size of the program, and then you want in your testing to try all possible test inputs within those bounds. Yes?
These goals appear to be also desirable by compiler developers. Right? Compiler developers also like to generate all these programs, just the compiler on them. So I was wondering whether somehow this aims a bit further than just testing the refactorings.
Yes, in theory one can use this ASTGen to test any other piece of code that takes inputs as programs. You can just use ASTGen to generate various kinds of inputs and run that. Now if you want to test compilers, that becomes a bit trickier because you need some way to check the output. And checking the output of a compiler is much trickier than checking the output of a refactoring engine. So yes, conceptually you can use this to test your compiler, but that wouldn't quite work. Another also issue here is that when you go to generate these programs, sometimes it may be very hard to generate the programs exactly as you want them. So suppose that we want to generate input programs, only those that compile. That may be fairly hard to express in this framework. So what you do then is you generate a larger superset of programs and then use compiler to filter out those that don't compile. See, so what I'm trying to say, if I want to test specifically compiler, I may have harder time using this because of the both output and the properties of input. Yes?
Doesn't a refactoring tool have to support partially correct programs that don't compile because the user's always in the middle of making changes?
Yes, they do support in the sense that they let you apply refactorings on the programs that don't compile, but usually that just comes with a big warning, and the tool just says, look, your program doesn't compile. Maybe I cannot even parse your program. I really don't know if you have, class A appearing somewhere where, my parser got lost, and I don't know whether there is A there or not. If you want me to replace A with airplane, I may easily miss that. I cannot give you any guarantee about that. So in most cases, I would say, I don't have any empirical data to support this, but I think that in most cases, developers actually apply refactoring engine only at the points where their code does compile. Because otherwise, if your code doesn't compile, especially if some parts cannot even parse, then it's very hard to know what guarantee are you going to get out of the engine. So all our testing was done with the inputs where that does compile. We still found many bugs, so I assume. If you go and test the cases where the input program does not compile, we'll presumably be able to find even more bugs, but it would be hard to describe even what the correct behavior of the refactoring engine is in those cases. So going back to this, we do this bounded exhaustive testing, and the goal is to catch the corner cases. The reason why we want to try all possible inputs is to catch the corner cases that may be there. And then last but not least, we wanted this to be composable. Again, the idea is that you write these generators that can create the simpler parts of inputs, and then from there you can build the larger parts. Here's then how the whole testing process looks like if one wants to use this ASTGen. First, the tester has to manually write a generator using this framework. Then the tester kind of instantiates this generator typically by providing some bounds, maybe how many classes you want to have or what their relationship should be and so on. And then there needs to be some driver code that actually runs this whole thing in a loop. So here's an example of this driver code, how this looks like. So here we will need to create some generator. Say if we want to encapsulate some field, we would say we want to encapsulate the field F, and then we need some generator that can actually create the programs that do that. And then there is a small just kind of piece of scaffolding code that does this. So we get some refactoring that encapsulate field, and we tell it to encapsulate the field F, and we perform this refactoring on the input program and then just check whether the output actually satisfies the required properties or not. So let's see now how an example generator looks like. This is sort of really the key part of the framework. The idea here is that, again, tester has some intuition of what kind of test inputs may show bugs. And sometimes you can express this intuition in, fairly easy in English. You can just go and write 2-3 sentences of describing a set of input programs. But it's very hard to actually go and manually write all these programs that satisfy this. So this is a particular example from our testing of encapsulate field, some generator that we call the double class field reference generator. And there is the short English description of that. So I want to produce input programs that have 2 classes that are related in various ways by containment and inheritance. And then one class should declare the field and the other should reference the field in some way. So here down we can see some examples of the programs that satisfy this description. So we have 2 classes A and B. They may have various relationships like subclass or inner class and so on. And then they're referencing these fields in various ways. So here we're only showing 3 examples, but of course the number is much larger. In theory the number is unbounded because we can just reference the field F in an unbounded number of ways in various expressions. But even if we put some bounds, if we say we want to have the nesting depth of these expressions up to some bound 2 or 3, it's still going to end up with thousands of these programs. And then the question is, how can we go from this English description to these thousands of programs? We don't do anything with English descriptions. We don't, try to analyze natural language. We actually ask the tester to express these properties directly into the code. So here are some kind of the parts of this description. So we want classes that are related by containment or related by inheritance. We want one class to declare a field, and then we want the other class to reference the field in some way. So each of these parts effectively corresponds to a large number of ways in which this can be done in the programs. And then for each of these parts, we actually go and build a small generator that just focuses on that one thing. For example, if we want to discuss the containment between classes, we would build a specific generator that just can generate all these different possibilities. Maybe either the classes are independent, or it's an inner class, or some method class, and so on. If you look at the inheritance, we can again generate all possible ways in which one class can inherit from the other. It can be again unrelated, or a superclass, or a subclass, or related through interface, and so on. If you want to declare a field, there are many ways in which this field can be declared. It can have different types, it can have different visibility, and so on. Again, we build this field declaration generator that can go and enumerate a large number of these expressions. And also, if you want to reference a field, there are various expressions in which we can reference this field. And again, we go and build a small piece of code that can produce all these pieces of abstract syntax tree. And now in order to test our program, what we want actually to do is to get a cross product of all these possibilities. We want to generate all possible programs by combining these things and then testing the refactoring engines on the resulting programs. Yeah?
On one side, I have the impression that basically, it's a generator for all kinds of programs. And here you're showing me 4 pieces that constitute programs. On the other side, and I see names like A, B, and every field is called F. Mm-hmm. So to what extent do you restrict actually what you generate? Are all the names hard-coded?
Okay, so the question is whether the names are hard-coded. You could hard-code them, but they're not necessarily hard-coded. Typically, the names are just given as some parameters here. So if I build here, a generator that actually creates these programs, I can pass the field name as the parameter in there.
And then there will be no field not called F?
If you're generating only one field and you say to be F, then in all programs it would be called F. Did I answer that question? It would never generate a field G unless you have a different generator that goes and generates something else. Here you would also give the names of these classes, A and B, because some programs you may want to generate things with 3 classes, right? So if you want to generate something with 3 classes, presumably they would be called A, B, and C, but you may want different relation between B and C and A and C and A and B, so these are then parameters that you can just give here. Yes?
With respect to unit bug and the way identifiers are handled in the refactoring, could you have a identifier generator that then would add to the cross product, so it would affect the identifier creation of all these guys?
Yes, yes, one would do that. So the field declaration generator, I guess, takes the parameter which is the name of the field to generate, and then what are the possible types to put there, and maybe what are the possible visibility and so on, whether there is also initialization for this field and so on. It's much more involved than is just shown in this example. So basically each of these generators takes a number of sub-generators for generation. So field declaration generator takes one generator which says what are the types to generate, another generator which says exactly this that you asked, what are the identifiers to generate for the field names, yet another one for possible visibility and so on.
That's also used by these other guys, the same identifier generator?
Yes, then you could pass that same identifier generator, say, as in here, in the one that generates reference fields, and say, if you're generating, say, F and G, then it would generate here F and also G and this F and this G and this AF and this AG and so on. Yes?
How do you handle dependencies between the generators?
That's an excellent question. So once we start combining these things, the problem is that there may be dependencies there, and that one thing can depend on the other, right? So if I generate here F or G or some other field name, then when I want to generate here an expression that references there, I better use the same identifier. Otherwise, I'm going to create a program that doesn't compile if I have here super.g and there I had int F. So the way that that's done is that you need to build these dependent generators. And now the things become a bit trickier to express and to, especially to put the generation in the right order, because now this means you first have to iterate this one to produce the values, and then you need to iterate this one to refer to those values from there. But in general, then the problem arises when some of these compositions may be invalid. Say, you cannot take this particular containment of classes and then this particular inheritance between classes, because you're going to get something that doesn't compile. And then there are various solutions there. One is this going into dependent generators, which means you spend more kind of work to describe what's proper and what's not. And then another sort of the easiest solution is just delegate this to compiler. And that goes back to this question whether you could use this for testing the compiler. The problem then is you would need to spend more time to describe all these dependencies here. And if you want to avoid that, if you kind of want to be lazy, then you just make the generator that produces things that don't necessarily compile, but then use compiler to filter that out. Yes?
So this is very heavily language testing dependent. Do these same kind of composable cross-product principles apply to data generators also?
Yes. I claim that that's possible to do. So I've done some research on that before, just not using this particular kind of generators, not using this ASTGen, using something else that we called Korat, and basically generating the complex data. We've done that things for, say, testing things like basic data structures you may want to generate, binary search trees or red-black trees and so on. And then some of those things have been also used at Microsoft for testing various things. I don't know what. They've used it for generating some XML documents and other things. What were the other things?
The serialization code?
parts of the serialization code and so on. So a number of things that were done also here where some data was generated using somehow conceptually the same ideas of these, what I like to call test abstractions, or we can call them model-based testing or something, where the idea is describe a set of test inputs and somehow the tool generates them. Of course, then the question just becomes how do you actually describe this set of test input and what's the language that you use that and how does this tool generate them.
And so did you implement all three or just the compiler?
I didn't implement any. It's the students that go and implement all of this. So I just wave hands. No, all these three things kind of are supporting the framework. There is this thing with dependent generators. I'm not going to go here much into the details of how this actually works, but the way this is done actually in the design of the generators, it distinguishes two phases. One phase is how to iterate to the next value. So during the generation, you kind of need to tick this. Suppose that I chose first this, and that. Now I need to go to the next value, which means I need to move one of these guys to go forward to actually try the whole cross product. And so you need to move this forward, and then as you move forward, it may become immediately illegal to combine these two things. So if this field F is not actually in this class, but it's somewhere else, and you don't have field F, then you cannot generate this. So one thing is how to move forward, how to describe what should be moving forward. And then the other thing is, if you generate these pieces, how to combine small pieces into larger pieces. So what the framework does is actually that it distinguishes these two concerns. One is the iteration, and the other is composition. And what that actually allows is to make some of these things here easier and for these dependent generators. Taking much more time to describe this, so we can take this offline, and I can show you some of these things. But basically, the framework supports all of these things. So you can write some kind of filters, manually write the filters that just throw things away as soon as they are generated if they are invalid. Or you can force the generation to only produce valid things, or you can just eventually delegate everything to the compiler. There's a trade-off between the amount of work that you spend on writing the generator versus the generation time. Because if you wait for the compiler, then you may just be wasting some of the time and throwing stuff away, but you just kind of wait a bit more. So that was all about inputs. I'm not going to go into more details, but I'll be happy to discuss this offline. So the other thing that we needed to do was about oracles, which is to validate whether the outputs are to validate the outputs of the refactoring engines. And of course, then the challenge there is that we don't know the expected outputs because we are automatically generated inputs. This is the case whenever you automatically generate inputs. Another issue is that sort of at its base, kind of the refactorings require that the output program be equivalent to the input. So this is of course undecidable by itself. But the thing is that our problem is kind of even harder than this. It's even different than this. Not only that we cannot check this in general, but we want to actually check that the structural changes were made. As in that example with the field F, if you do want to encapsulate the field F into setter or getter, you want this actually to be made. So question is how to do that. So as I said, we've just built manually a number of oracles for that, ranging from simple things, whether the refactoring engine crashes altogether, we never found any bug there, to the things whether the output program compiles, and then whether we are getting appropriate warnings from the refactoring engines, because remember, it need not always generate the refactor program. It may sometimes say, I cannot refactor this. Similar like your compiler would say, you have a compile error, and so I cannot generate some assembly code or whatever other code that it should generate. Then there were also a few interesting things that we did. For example, these with the inverse refactorings. So many of the refactorings you can kind of apply the other way around. So if you rename A to B, then we can rename B to A and hopefully get the same input program. So what we want to do then is to check, if you start from some program, rename A to B and rename B to A, that you are getting the same thing. Of course, you need not get exactly the same thing, even at whatever level, right? So if you just even print that out, it may not have exactly the same files, exactly the same sequence of characters. Even the ASTs for that may not be exactly the same. So we need to build some tool that kind of tries to compare these ASTs by ignoring some of the details. maybe the order of methods would be different, or maybe the new name that was chosen, the fresh name that was chosen in some rename would be different, and so on. So you need to have a comparison that kind of ignores some of that stuff. And then there were some custom oracles. For example, if you apply encapsulate field, you want to check that there are no more references to the field except for the setter and getter. And then last but not least, we did this differential testing. Basically, you get the same input program, you give it to both Eclipse and NetBeans, and then you check whether you're getting the same output program or not. Of course, even there, the same means modulo the sum of the changes that you tolerate.
So,
yes?
so if you have a refactoring engine which does nothing, it would pass all the tests.
Well, it would presumably not pass this one, custom one, because you would check for certain structural changes and you would find that it didn't do. And then also you hope that here, out of these two refactoring engines, at least one of them does something, and then that one would have a bug.
But
yes.
Nothing of the oracles involves actually running the program and seeing whether the input-output behavior changes.
Yeah, these oracles that I'm mentioning here, not, but we had also experimented a bit with that. That becomes much more complex because now you have automatically generated programs for which you want to automatically generate tests, and then you want to refactor the program and run these tests. So becomes a bit trickier. We just had, I think, one experiment with that, but we did not pursue that too much. I mean, these are all good questions. I guess the thing was that we still found a lot of bugs even with this stuff that we did. So that's why we didn't pursue some more things on this. So here's then basically what we did with this ASTGen. We tested this Eclipse and NetBeans. We tested 8 refactorings, I guess, from each. They target various program elements, fields, method, classes. We had things like encapsulate field, move method, rename class, and so on. So we had about 50 generators, some of them for very small ones for generating the small parts of the ASTs, and then some complex ones for building entire programs. And we've actually found 47 new bugs. So we reported these bugs. And then we've done some comparison of these, how good these oracles are and how well the generation works. So here are some of these results for the generator. Say for testing this encapsulate field, we've written a number of generators that generates various programs. So I guess the one that we used as the example was this double class field reference. So if you run that, it can produce a number of inputs, so some of them in hundreds or thousands. Here was the time taken to produce all those inputs and to run refactoring engines. And then here was the number of bugs found in the refactoring engine. So what we found then overall was that this generation time and compilation times were much smaller than the refactoring time, actually running the refactoring and checking the oracles. So generation by itself was not that big problem, but this execution of refactorings was actually taking a lot of time. So that's as far as the machine time goes. And then as far as the human time goes, some of the initial experiments that we kind of tried to track how much time it takes to build one of these generators, this took about 2 work days. But this was really still the initial phase where we were not just saying, okay, we want to build this specific generator, but we were still also developing the library and not only writing some specific generator, but also writing the small sub-generators that we need. So nowadays that the library is much bigger and there are many things that you can reuse, so it takes about 2 hours to write something like that. So it takes about 2 hours to write one of these, and in turn that one can produce this many input programs. Yes?
How many of the generated input actually compiled?
I don't have that number with me here, but again, that's in the paper. I believe about like one in 3-4 would compile. I think it all depends, specifically what the generator was doing and so on.
But overall, it seems that so the key thing to do was to write these 5 generators, which basically found most of the bugs.
No, so the way it went is, so this table is much bigger. So there are many more refactorings that we tested, and for various refactorings we would have more generators and so on. The thing why we had sort of the most generator for encapsulate field was because, as I said, once you start finding some bugs somewhere, then you kind of figure out that there may be more bugs there. So we found some bugs in the encapsulate field, and then just figure out that probably that this refactoring just not as robust as these. Actually, you can even see that the simple way, this one was built maybe 2-3 years ago, whereas these are 7-8 years old. So these ones that are older did not have any bugs. Actually, here in Eclipse, we did not find any bug with rename. At least for these generators. It does not mean that some other generator could not find a bug. We did still find one of them for NetBeans. But for this encapsulate field, we would just find bugs with almost any of these generators. And just at some point, you stop writing any more of these generators. And probably we could find even more bugs there. Yes?
So this number of bugs, does it mean a test that failed or an actual bug?
So this is an actual bug. Actually, the way it goes, let me just see if we have this number here. Yes, so here's a number that shows a bit more of what happened there. So you've seen that we can generate like hundreds or thousands of test inputs. When we run them, we can still get a large number of failures. What this table here shows is the number of failures for various oracles. WS, I guess, was warning status. This DNC does not compile. So if you give a program that compiles, we run refactoring engine. If you obtain a program that does not compile. So as you can see here, for this particular case, let's say this double class field reference generator, I think we were generating about 4,000. That was this on the previous slide. So here we are generating 4,000 of them. And then once we run that, we would obtain a few hundred of them that actually fail. So we would get 187 of them that fail, this does not compile, and 100 more that fail this custom and inverse oracle, and 500 more where Eclipse and NetBeans would differ. So this was the number of failures, but then the actual number of bugs was only this. So the number of bugs that we reported in the bug tracking systems for Eclipse was just 1. And so the issue then here is that you can get a large number of failing tests that are actually due to the same underlying cause. They are due to the same bug. And one needs to sort of address that, and that's part of ongoing work, so I have a few slides there. Does this answer the question?
Yep. Okay.
So, yes?
So you're saying all of those failures were the result of one bug? There aren't any sort of hidden, once we fix that bug, there's going to be...
So in this particular case, now again, I don't have the data, but it may be that we found more. So the numbers in this column are what we reported in the bug database. We did not report the things that were either fixed in a later version. So all of this, our work was done in a bit older version. We need to get some old version to fix that version and to build this whole thing about automatically running and so on. There needs to be a lot of engineering to actually get this thing to run this whole stuff automatically. So at the time when we would find some bug, we would check against the newer version whether it was already fixed or not. And we were about 6 months or so behind. So they would already fix some bugs. So that was one thing. And then sometimes we could find here a bug that was already reported previously. So even if it was not fixed in the current version, it may have been reported. So we did not just want to go there and report duplicate bug reports. So then what this column shows is just how many we actually put there in their bug tracking system. We did find some more. Now I don't have again the numbers on this slide of how many more we exactly found.
So from the perspective of how many bugs does this approach find, the one is not really representative?
It's slightly more than 1, but not much more, maybe like 2 or 3. So it's not like, oh, it found 20, but all those 19 were either fixed or reported. Maybe it's just slightly more than what's shown here. They're all good questions. Any more questions?
I was just curious about the number of open bugs in each of those, the Eclipse refactoring engine and the NetBeans. Like, just to give us a perspective, like, are there just 10 open bugs and you added 21, or are there 1,000 open bugs?
I think probably on the order of 100, but again, I would not know the exact number. Actually, it's very hard to search through those bug tracking reports. We wanted to do even simple things like this. Find which of these refactorings had the most bugs submitted in, say, last 6 months. Presume, that one is, say, the least robust, and maybe we want to focus our testing effort on that one. So even asking these simple queries is actually fairly hard to get the numbers. So what they use, Eclipse uses Bugzilla for their bug tracking, and NetBeans uses this IssueZilla, which is very similar to Bugzilla. So asking even these simple queries is actually fairly hard. Of course, one can just go and search by encapsulate field, but then you're going to miss some of them, and some people just don't use encapsulate field refactoring, some refer it in some other name, and so on. So improving this bug tracking system is a challenging and important problem. So it's being able to better search through that. Sometimes if you just want to find, say rename method, this is fine. You can just search for rename method and find that. But we wanted also to find some things that are kind of, cross-cutting. Say we want to find all bug reports that say that an incorrect warning status was generated, regardless of which refactoring, but we just want to find incorrect warning status. And this one is almost impossible to find unless we just go and download all the hundreds of the bug reports that are open and someone goes and manually inspects that. But I think that the number of open reports is maybe on the orders of 100 or so. And that, of course, depends for all the refactorings. They have, Eclipse has, I think, about 24 or so, whereas we only tested 8 of them in our approach. And NetBeans has maybe slightly fewer, maybe about 15 or so of refactorings. So here then the results that we obtained by running this, so we got these 47 new bugs, so 21 in Eclipse, and so they confirmed 20. And then 26 were in NetBeans. So they've confirmed 17, and they've already fixed 3. They put that one they don't want to fix, although we still think that this is incorrect. And then this is, I guess, what made the students furious, that they reported some of the bugs were duplicates. Because the students spend a lot of time actually looking whether the bugs are duplicates or not, just kind of doing their best effort to make sure that they're not reporting something that's already there. But then the triagers or developers, whoever on the NetBeans side, just came and said that some things are duplicate. And we still think that even that they're wrong there, in the sense that if they go and patch whatever that they said was duplicated, that's not necessarily going to patch the actual bug that we reported. That would be very hard to evaluate. We need to wait for them to actually go the patch duplicate and see whether they actually patched our bug or not. And as I said, we did find some more bugs, but did not report them because they were either obvious duplicates or something that was reported previously, or they were already fixed by the time we found them. And then what's interesting here in these results is that these parts of the ASTGen are now being included in the NetBeans testing process. They started adding that to not only have their manually written tests, but also to add some infrastructure to be able to run this. This is still not finished, but they've started some things on that.
What did you mean by this one won't fix?
So they said for one of these bug reports that they do not want to fix it, even though it's incorrect. I happen to remember that one. It was something related also, I think, to encapsulate field. The problem there was that in most cases, when you put this setter, the return type is void. But in some cases, that are again fairly tricky, the return type of this setter needs to be the same as the type of the field. So you would need to put here int setf. The reason why you need that is because you can create this kind of weird expression where the assignment is actually a sub-expression of something else. So therefore, the assignment not only needs to make the change on the state, but also needs to return the new value. So you would do this f gets f and then return this dot f, and this needs to become int. And what they said is they don't want to fix that because if they do that, that would violate some issues, whatever. When you build these Java beans, then the setters have to have void, otherwise reflection cannot find them. But the problem there is their fix should not be, we will change the way that we do encapsulate field. But the fix should be, we should raise the warning and say, if you have an assignment as a sub-expression, the refactoring engine should say, I cannot do encapsulate field because you have an assignment as a sub-expression. But now they just said they don't want to fix, and what that means, if you have assignment as a sub-expression and you go apply encapsulate field, you get something that doesn't compile. Now this is an easy bug. You can just go and immediately sort of revert the refactoring and just say, okay, the refactoring cannot apply, I'm just going to do it manually or something like that.
What does Eclipse do in that case?
Eclipse creates an int here, so it would just put, int setf and add here return this dot f. It just creates a setter that also returns the new value.
In general, sometimes, so when they fix a bug, could it simply be then that instead of generating something that is wrong, now they give a warning?
Yeah, they could give a warning. Actually, what we found is that NetBeans is much more, much less aggressive in trying to apply refactoring. NetBeans much more often gives warning and says, I don't want to proceed with this because I could do something wrong.
So that would be the perfect refactoring engine?
Yeah, yes. A refactoring engine that always gives you a warning and says, I could do something wrong if I proceed, would satisfy probably all your requirements. Except it would be useless. If one of your requirements of software is to be useless, then it would satisfy even that requirement. Yeah, but at least it would be correct. According to our thing, we would never find a bug there. I mean, what we would find is that there is some difference. Right? When we run this on the same input program of both Eclipse and NetBeans, Eclipse proceeds, but NetBeans doesn't. Then we need to go and manually inspect why and what's the difference. And should Eclipse said also I should not proceed, or should NetBeans be more aggressive and actually proceed? Best, at least in that way, you are not kind of introducing the bugs that could trick the developer by creating some hidden things somewhere. Okay, any more questions about these things? Yes?
Just one more question on the invalid input generation. So did you guys spend any time looking at why the compiler wasn't able to compile some of these? Because you're trying to generate pretty structured programs, right? You're not deliberately introducing errors into them or anything?
Okay, you mean if in this our own generation, whether we looked at this thing, you mean why are the inputs that we generate, why they cannot compile, right? We spent some time on that. That's how we were building even these dependent generators and adding some of these filters, but we did not spend too much time on that because eventually, yes, what we would like to do is to only get the programs that compile. Like maybe someone wants to test the refactoring engine with programs that don't compile, but still, if we have some properties in mind, we want to generate test inputs that satisfy those properties.
Okay, so it's not a big deal that you might not be generating really complex inputs that satisfy the properties as long as you're generating some input.
Well, I would actually say that it's a big deal. I mean, it's something that we should spend more effort on. If I want to generate test inputs that satisfy certain properties, I only want to have those that satisfy properties. Here we had an easy solution, sort of, we want inputs that compile, but even if we get something that doesn't compile, that's fine. We run through the compiler and it just throws that away. But the question is, what if you really wanted to generate things that, do compile, or you wanted simply to generate things that satisfy certain properties? How can you easier express that in here? That's kind of part of a future work, so it's not that we have a final solution for that. So here's also some work that we have, ongoing work. So we're working trying to reduce the machine time and the human time in using this ASTGen framework. So the machine time is kind of for generation and execution of these test inputs. Of course, machine time by itself wouldn't be all that important, but the issue is that this machine time actually translates into the human time. So if I write one of these generators, as I said, nowadays it takes about 2 hours for the students to write one of those. If I write a generator and push some button and say start testing now, if I need to wait 1, 2, or 3 hours to get back some result, then the developer is just kind of idling, developer or testing, because you are just waiting back for the result. So that's one part. And then the other thing is just the human time for inspection, because as we discussed, you can get hundreds of programs that fail, but they only have 1 or 2 actual bugs that are there. And so here then the things that we are doing, one thing is we want to reduce the time to first failure. So rather than exhaustively trying all possible inputs, we try to kind of skip through some of them. We just go and skip through a number of inputs and try to quicker find some that fails. And then if this kind of sparse generation does not find anything, then we go and proceed exhaustively. We also want to reduce the test generation and execution time. So here we are trying a smaller number of larger tests. Rather than generating large number of smaller tests, which we had one class and only one expression, here we want to try one class with many expressions. And then to reduce the time for inspection, we have some Oracle-based clustering. We try actually to group the tests together based on the Oracle messages such that they hopefully have the same underlying bugs, just so that there is less to inspect there. Actually, results are quite promising. Here we can save the time sort of an order of magnitude. Here it's also like 2, 3x. And here we can significantly save this time. And we can sometimes merge 100 failing inputs and just say these all seem to be due to the same bug. So you only need to expect 1 or 2 from here rather than all 100. So here's kind of the future work, the things that can be done. So specific to testing refactoring engines, we can of course always try more refactorings, try different refactoring engines. Maybe someone wants to try this for Visual Studio. Some people have actually used the ASTGen. Recently there was a paper presented at UPSLA just, I guess, 2-3 weeks ago, where they've used ASTGen to test their own new refactoring engine that they built. Then we can apply this ASTGen to other program analyzers, basically anything that takes programs as input. We've already done a small study with a tool called JavaCop, developed by Todd Milstein at UCLA. And so we found a small bug there. Then the other things that can be done is to reduce or eliminate these false alarms, something that I didn't even discuss, but because of this comparison of ASTs, we don't always get the correct results. We have some false positives there. And then to reduce these redundant tests rather than have 100 failures to just maybe show only 1. So this is specific to refactoring engines, but then more general about the test abstractions. The idea, remember, of test abstraction is that you want in some language, you want to describe a set of test inputs. Rather than manually generate one by one, you describe the whole set. So the research there is along the lines of what are the languages that make this easier to use, how to better describe these sets, and how to generate them faster. And of course, always to improve these oracles and clustering. This is, I guess, what we are also finding to be very important. I mean, now we can find many bugs, but now you have still many tests to inspect and many failing tests. So how can you reduce even that effort, even at the expense of maybe missing one bug here or there, but at least to reduce that effort? I mean, it's very hard to go to read to these 100 programs and just try to figure out are they due to the same bug or not. Here's then the work about test abstraction, basically asking the question how to describe these tests, what to generate, how to generate, and so on. And here's then the conclusion. We applied this to refactoring engines. We found some bugs, and the code is publicly available for download there. Okay? Finishes the talk.
And so Darko will be here for the entire week for the history conference on the Microsoft campus. So he's around, and he might be able to meet with you if you want. Okay.
Thank you.